Modern life runs on semiconductors, and TSMC is arguably the most important fab in the world. It makes around 90% of the world's most advanced chips. Now TSMC has announced a new technology that will take us beyond 1 nanometer. As a chip designer, I can tell you this is a big deal for the entire industry. So in this video, I will break down the genius behind this new technology. What is the next big thing in semiconductors? What's going on with the TSMC stock price? And why we will rely less on ASML lithography machines in the future. When TSMC was starting out in 1987, their first chip was manufactured in 3 micrometers technology. That's 3000 nanometers. Just think about it. And recently they announced that they are ramping up the production of 1.6 nanometer technology. This means that over the last 40 years or so, they managed to make their chips 99.99% smaller. And the next big breakthrough is just around the corner, and it involves new materials and a cutting-edge transistor architecture, CFET. But to truly grasp the beauty, the genius behind this, we must start with transistors first. If we go back up until around 2012, the basis for all silicon chips was so-called planar transistor. And we love planar transistor because this one is very easy to understand. It's just like a tiny electronic switch which controls the flow of the current. Imagine a pipe with water flowing through it. If you place a valve in the middle, you can turn the water flow on and off. In a similar way, transistor controls the flow of electric current. It has 3 main parts: source, where the electric current starts, drain, where the current exits, and gate, which is used to control the transistor. When you apply voltage to the gate, it creates an electric field that either opens or blocks the path between the source and the drain. So this planar transistor remained the state-of-the-art technology for about 50 years. But when we were approaching the 22 nanometer process, scaling its dimensions further were no longer possible. What's interesting, for a long time we were reducing the gate length, but further reduction were causing the channel becoming too thin, which resulted in electron tunneling from the source to the drain. And that's bad. Imagine, in the example of the pipe, imagine you close the valve, but the water is still leaking. So basically, we were not able to control the transistor anymore. And as you'll see today, since then, it has become all about the gate. The first step in this evolution was to stretch the channel in a kind of fin and wrap the gate on 3 sides of it. This new architecture was called FinFET. And this was a very elegant solution because the gate wrapped around the channel allowed for better control it. It means it could be faster switched on and off, quickly improving the speed of transistor and allowing us to pack more of them per silicon area. These new transistors leaked less power when they were switched off, means devices can run longer on a single charge. In fact, Intel was the first to manufacture FinFET devices, which hit the market in 2012 at the 22 nanometer process node. And 1 year later, TSMC also moved to FinFET devices. In fact, today, almost all high-performance electronics, including Apple Silicon, NVIDIA and AMD GPUs, are manufactured in FinFET technology. Now we are coming to the most interesting part. As of today, the limits of FinFET architecture has already been reached, and now the industry has to take yet another bold leap in transistor architecture. Now we are entering the truly 3D era of transistors. And remember, it's all about the gate. If you think about it, the only way to shrink the footprint further and get even better control of the gate is to control it from more sides. Here, the genius is in turning the channel on its side, stacking horizontal nanosheets instead of standing vertical fins. Now, instead of growing horizontally, the nanosheets are multiplied vertically, And this design allows the gate to fully wrap around the channel, so a true gate-all-around structure, eliminating leakage and improving electrostatic control. And good news, the first gate-all-around transistors are coming in N2 technology, is already entering the mass production, and first devices coming to iPhones. Now, let's talk tools. Even though gate-all-around architecture was an evolutionary step from FinFET, where TSMC was a decade-old leader, still many processes had to be readjusted. And here the general trend is that from now on, EUV lithography machines will be less on a critical path, and other tools and novel materials will become more and more increasingly important. EUV tools essentially create a controlled, tiny explosion inside the machine and use the high-energy emitted photons to print the finest features on the wafer. And this process is beautiful. It's often compared to tiny star explosions because there is a similar process behind it. It involves extremely high temperature plasma generation, similar to what happens in the sun. If you look at gate-all-around architecture, the main challenge is to create the channels and wrap the gate around it, especially when you can't directly see the underside of the nanosheets. That's where atomic layer deposition and epitaxy growth become critical. It's crucial here to precisely deposit gate dielectrics and metal gates around these intricate shapes. And for these steps, Applied Materials and ASM, not ASML but ASM, own the secret sauce. What's more, after the deposition, we have to etch away the material in between the channels. And here, lateral etching tools from Lam Research are critical. And finally, we need one more deposition step, where the gate around the channels is formed. And here, again, the tools from Lam Research and ASM are critical. So this is the elegant solution behind today's state-of-the-art gate-all-around transistor architecture, which is mostly about going vertical, and this will enable shrinking beyond 3 nanometers. What's interesting, we had planar transistor for 50 years. And then we had FinFET as the state-of-the-art for a decade. How long gate-all-around will last? After roughly 30 years in the making, probably 5 years or so, just one of many examples where we see everything accelerating. Technological progress is accelerating. As Ray Kurzweil said, we won't experience 100 years of progress in the 21st century. It will be more like 20,000 years of progress at today's rate. I totally feel that. Do you? We all know that AI can help us now to create things faster than ever. And one of the most exciting shifts is happening in the software development. What if I tell you that I managed to create a custom-made web app with just one click, without a single line of code? With Hostinger Horizons, you can turn your idea into a fully functional web app using AI-generated code. No coding, no complicated deployment, no third-party hosting, just a couple of clicks and you're alive. Here is how it works. Simply type your web app concept into the AI chat box and watch as the AI instantly generates the first version of your app. And in case you need any changes, you can quickly tweak it with AI assistant edits. When it's ready, you can instantly publish your app, domain included. What you can do with it in just a few clicks is mind-blowing. So whether you're a founder, an entrepreneur like me, or a micro SaaS startup, Hostinger Horizons gives you all-in-one solution to build and deploy your software. On top of this, Hostinger offers a 30 days money-back guarantee. So why not to give it a try? Use my link in the description below and apply my code Anastasia10 to get 10% off your first month on Hostinger Horizons. Thank you, Hostinger, for sponsoring this episode. Now, we discussed the current state of the art gate-all-around transistors and that controlling the gate is crucial. And we are coming to the most interesting part, the next big thing in semiconductors. How can we build even smaller and faster transistors? What's interesting, TSMC is currently working on two parallel tracks, horizontal and vertical. Let's start with the vertical one. So the genius of the new architecture lies in details, in the new stacking approach. Instead of placing transistors side by side, the new architecture consists of a vertically stacked PMOS transistor on the bottom and NMOS transistor on the top. And this cuts transistor footprint by half and keep Moore's law going. And this new architecture is called CFET. Complementary FET transistor. Other companies calling it differently, but the idea is the same. The next big thing in semiconductors is a vertical transistor. The bottom layer contains a P-type gate-all-around transistor called PMOS. When a negative voltage applied to the gate, it creates a channel of holes, allowing current flow. And the top layer contains an N-type nanosheet transistor. And here, a positive gate voltage creates an electron channel, enabling current flow. Both NMOS and PMOS nanosheets are surrounded by gate material, forming a gate-all-around structure. These sheets are typically very thin, around few nanometers, and narrow, around 10 to 15 nanometers. What's interesting, one of the key persons responsible for the CFET development at TSMC is Sue Lau. She is a director of device architecture pioneering at TSMC, and she joined TSMC in 2021 after 16 years working at Intel, where she contributed to all the latest development from 65 nanometers down to 4 nanometer process. Now, at TSMC, she is pioneering new device architectures, such as CFET, while at the same time looking into the integration of novel materials, which we will discuss in a moment. Her recent paper describes the first working CFET device, and is a pretty remarkable achievement. Recently, at the latest International Device Manufacturing Conference, TSMC presented the first working CFET, and they managed to solve the interconnect challenge to interconnect the bottom and upper transistors. And it seems that TSMC is leading CFET development and being ahead of the rest of Samsung, Intel, and even IMEC. The main challenge with CFET is interconnect complexity. You know, interconnect, those tiny fine metal lines that interconnect all the transistors and other electronic components on the chip. Usually it's a complex metal network of up to 20 layers that enable data transfer and power distribution across the chip. And in modern chips, interconnects run mostly in horizontal layers across the chip. Now, with CFET, the connections must go vertically, which again increases the resistance, capacitance, and add additional delays, slowing the signals down and increasing power consumption. Adding complex vertical interconnects means more processing steps, new alignment challenges, and potential defects in wiring. And it would probably require backside power delivery and potentially even backside signaling for the PMOS transistor. Not to mention extreme thermal challenges that are coming with this new architecture. Already now, the high-performance NVIDIA GPUs generate several hundreds of watts per square centimeter of silicon, and is projected to reach 1 kilowatt per square centimeter of silicon. Now imagine what will happen when we pump 1 kilowatt of power into this tiny multi-layer transistor piece of silicon, which is a part of a 3D package. It's gonna be hellishly hot. So CFET approach to scaling is genius, but it comes with a whole new set of manufacturing challenges, more processing steps, higher cost. At the moment, it's expected to reach mass production in roughly 2030, and this will allow us to scale the transistors beyond the 1 nanometer node. As you saw, in the early days of the transistors, innovations were primarily focused on geometry, but now the focus is shifting. Now, TSMC is pushing on the development of new materials, mostly focusing on the 2D materials, with the goal to use them in the channel of the transistor. You remember early in the video we discussed the problem which arose when we tried to shrink the planar transistor, the gate of the planar transistor further. This is the limitation of silicon. That's why researchers are now focused on other materials to push the performance further. It turns out that 2D materials are more robust to the effects causing leakage and much easier to control in general. TSMC is mostly focusing on TMD materials. I will put them on the screen. And these materials have the potential to enable atomic thin channel transistors. But those are still mostly in the research phase and still quite far from commercial use. And the main reason for that is the growing process of 2D materials. Currently, they are grown on the sapphire wafers and then transferred to silicon wafers. And this is not scalable for mass production. To enable the mass production, we have to learn how to grow them directly on silicon wafers. In fact, I have about 3 to 4 episodes on this channel about semiconductor material innovations, covering 2D materials, indium selenide, graphene, and other materials. So subscribe to the channel now so you can enjoy them later on. Another big shift worth mentioning in this episode is towards material innovations. And if we look at the N2 process node and also all the innovations we just discussed, we see that the trend is that the focus is shifting from lithography tools towards other processes and mostly material innovations. To be clear, EUV lithography tools will be still important. What I mean is they will be less on a critical path towards future transistor scaling. Over the past few years, we talked a lot about EUV lithography machines, and that's because they were crucial for transistor scaling. And as transistors were becoming smaller and smaller, the interconnect, which connect all these transistors into logic gates, all of this had to also scale down. In fact, transistor scaling was always outpassing the interconnect scaling. Let's say at 7 nanometers down to 3 nanometers, EUV machines were the most critical tool for scaling. Because older DUV machines, deep ultraviolet lithography machines, which use longer wavelength light compared to EUV machines, were not enough to pattern the finest metal lines for the interconnect layers. But looking at the latest process nodes, like N2 from TSMC, its role is decreasing. It's decreasing because we are shifting to CFET architecture, which has its own challenges, and because we are shifting to backside power delivery, which is actually removing the congestion of interconnect on the top of the wafer. This shift to backside power delivery is a big change for the entire industry, because till now all the metal, so signaling and power layers, all were placed on the top of the wafer. Now the idea of the backside power delivery is to offload the power to the bottom of the wafer. So those metal lines, which are thicker and wider, which are used to deliver power, they will have to go on the other side, which will free up the space on the top of the wafer. And this means with backside power delivery, we can reduce the number of fine pitch layers on the top of the wafer. It means fewer exposure steps, fewer UV masks, and lower cost. And this is a big advantage for going beyond 3 nanometers. While EUV tools from ASML are less on the critical path, TSMC remains the most critical fab that the entire world depends on. So then, what's going on with TSMC stock, why it has gone about 15% down over the last few months. One of the contributing factors is concerns over potential US tariffs on computer chips that could reach as high as 100%. Well, I think it's a part of Trump's strategy to encourage TSMC to build fabs in the US. And this is driving the stock down, which means shopping time. Because despite all these concerns, they show strong revenue growth, about 43% year to year, which shows strong, robust demand in silicon chips. Now consider the high costs required to building the cutting-edge fabs and also the costs of constantly upgrading equipment to staying on the leading nodes. No surprise that more and more fabs are dropping out from this race. You know, in 2007, we had 12 fabs manufacturing chips at 45 nanometers. And now we have come down to just 2 fabs fabricating silicon in 3 nanometers. And with Samsung and Intel recently struggling with yields, it's really just TSMC leading the charge. So the role of this company in the modern economy is undeniable. And a few days ago, TSMC announced their plans to invest another $100 billion to expand its semiconductor manufacturing in the US. For once, billions are coming in instead of other way around. That's a change. And this investment will be used to build 3 additional fabs in advanced nodes, 2 packaging facilities, and we know that packaging is so important for the advanced GPUs and in general a part of the success of keeping the Moore's law going, and they will also build 1 R&D lab. As you may know, they are already building 2 advanced chip plants in Arizona, with the first set to begin production already this year and the second planned for 2027. And this is a huge fab. It's hard to imagine how huge it is. It's around 1100x in size, which is roughly equivalent to 650 football fields. And this making this manufacturing facility one of the largest semiconductor production sites in the world. Anyway, I think the costs of TSMC chips will go up, whether as a result of high tariffs or higher manufacturing costs in the US. Let me know what you think in the comments. As Stephen Hawking said, we are standing on the threshold of a brave new world. What we do with our discoveries will shape the future of humanity. Clearly, the next decade in technology will be defined by AI and high-performance computing, which are demanding exponentially more computing power. And the key bottleneck is energy. We are currently hitting the limits of what our power grids can deliver and what our cooling systems can handle. Without power-efficient transistor technologies, our data centers will hit the power ceiling. And clearly, we need new materials and a breakthrough or 2 in semiconductor technology to keep up with AI power demands. I think it's rather going to be a complex solution, which means novel materials, new architecture of transistors, integrated cooling technology, including also backside power delivery, chiplet approach with photonic interconnect, and advanced packaging. It all has to come together. Let me know what you think in the comments. Now, check out our sponsors in the description below to support the channel and watch this video where I explain the backside power delivery, how it works, and the secret plan of Intel, or this video where I explain the new photonic chip which is on the way to data centers right now. And connect with me on LinkedIn. All the links are below. Thank you for watching. Love you guys. Ciao.
And that's it for today, guys. I hope you had fun watching. If you did, don't forget to hit that like button and subscribe to the channel for more awesome content. Thank you so much for watching and hanging out with me. I appreciate you all. I'll see you in the next video. Bye.